In this video, we discuss Cauchy's integral theorem involving contour integrals of analytic functions. We take a function f such that f prime exists and is continuous in a simply connected domain that we call D. We take a contour C that is completely inside D. Let the contour C be also simple and closed. The contour C is said to be closed if its starting or initial point equals its final or terminal point. If C is parameterized by z equals z of t, where t is on the closed interval from alpha to beta with alpha less than beta, then z of alpha equals z of beta. In addition to being closed, for a simple closed contour C, z of t sub 1 equals z of t sub 2 for t sub 1 less than t sub 2, if and only if t sub 1 equals alpha and t sub 2 equals beta. In other words, the only pair of distinct t values with the same z value on C is alpha and beta. The domain D is said to be simply connected if any simple closed curve such as C can be shrunk continuously to a point without any portion of the curve leaving D. If the contour C happens to enclose a hole, when C shrinks down to a point, somewhere in the process of shrinking, part of C will intersect the hole so that a portion of C will no longer be lying in D. Therefore, D as shown on screen is not simply connected. So if D is simply connected, then D should have no holes. Under these conditions, the contour integral of f of z dz along C equals 0. For a proof of Cauchy's integral theorem, let E be the interior of C. Let z be equal to x plus iy, where x and y are real numbers, and so x and y will be functions of t as well, so that x equals x of t and y equals y of t. Let f of z be equal to u of xy plus I times v of xy, where u and v are real valued functions. Since f prime exists, f satisfies the Cauchy-Riemann equations so that u sub x equals v sub y and u sub y equals minus v sub x. U sub x, u sub y, v sub x, and v sub y are the partial derivatives of u and v with respect to x and y. We replace f by u plus iv in the contour integral. dz equals z prime dt, where z prime dt equals x prime dt plus I y prime dt. And x prime dt is dx, and y prime dt is dy. Multiplying out and separating the real and imaginary parts of the integrand, the contour integral of f along C equals the integral of u dx minus v dy, plus I times the integral of u dy plus v dx. Assuming without loss of generality that C is oriented positively, we apply Green's theorem to each of these line integrals. If the real valued functions p of xy and q of xy along with their partial derivatives are continuous inside D, then Green's theorem says that the line integral of p of xy dx plus q of xy dy over the contour C equals the double integral over the region enclosed by C, and that region is E, of q sub x minus p sub y. In the first line integral, we set u equal to p and minus v equal to q, so that q sub x equals minus v sub x and p sub y equals u sub y. Therefore, the integral along C of u dx minus v dy equals the double integral over the region E of minus v sub x minus u sub y. For the second line integral, this time we set v equal to p and u equal to q, so that q sub x equals u sub x and p sub y equals v sub y. And so for the second line integral, we have the double integral over E of u sub x minus v sub y. This part of the Cauchy-Riemann equation says that the integrand of the double integral for the imaginary part is 0. And this part of the Cauchy-Riemann equations says that the integrand of the double integral for the real part this time is also 0. Therefore, these line integrals must be equal to 0, so that the contour integral along C of f is 0. Now, we take a look at two examples related to winding numbers and to Cauchy's integral theorem. For both examples, let the contour C be the circle with the parameterization z equals 2 plus 3 times e raised to the power it with 0 less than or equal to t less than or equal to 2 pi. For the first problem, we find the value of the integral along C of dz over 2z minus 2 minus 7I, which equals this integral, so that f of z equals 1 over 2 times the quantity z minus 1 minus 7I over 2, and f prime of z equals minus 1 over 2 times the square of z minus 1 minus 7I over 2. F and f prime are continuous everywhere except that z equals 1 plus 7I over 2. 1 plus 7I over 2 is clearly outside C because the imaginary part of 1 plus 7I over 2, which is 7 halves, is bigger than 3, which is the largest imaginary part of any z on C. This means that f and f prime are continuous in a domain that completely contains C. Therefore, by Cauchy's integral theorem, the integral of dz over 2z minus 2 minus 7I should be 0. We can also use the winding number of C around 1 plus 7I over 2 to find the value of the contour integral. This contour integral is 2 pi times I times the winding number of C around 1 plus 7I over 2. Since 1 plus 7I over 2 is outside C, the winding number of C around 1 plus 7I over 2 is 0, so that we also get 0 as we should for the value of the contour integral. For the second example this time, we find the contour integral of dz over 3z minus 8 plus I, or the value of this integral, so that the integrand is discontinuous at 8/3 minus I over 3. The viewer can check that the distance between 2 and 8/3 minus I over 3 equals the square root of 5 over 3, which is less than 3, so that the singularity 8/3 minus I over 3 is inside C. And so we cannot apply Cauchy's integral theorem in this exercise. This integral is 2 pi times I times the winding number of C around 8/3 minus I over 3. The circle completes exactly one counterclockwise revolution from t equals 0 to t equals 2 pi, so that the winding number of C around 8/3 minus I over 3 is 1. Therefore, the value of the contour integral of dz over 3z minus 8 plus I should be equal to 1/3 times 2 pi I times 1, or 2 pi I over 3. We can also find the value of the contour integral directly. From the parameterization, dz equals 3I times e raised to the power it dt. Z equals 2 plus 3e raised to the power it. We replace e to the it power by cosine t plus I sine t. And multiply things out so that the numerator equals the quantity minus 3 sine t plus 3I cosine t dt. We do the same in the denominator and separate the real and imaginary parts. We multiply the numerator by the conjugate of the denominator and separate the real part from the imaginary part of the resulting product. The denominator multiplied by its conjugate should be equal to 86 minus 36 cosine t plus 18 sine t. The integrand of the real part is the derivative of 1/6 times the natural logarithm of 43 minus 18 cosine t plus 9 sine t. And when we evaluate this antiderivative from 0 to 2 pi, the value of the integral for the real part turns out to be 0. For the integrand of the imaginary part, we found this antiderivative formula by using a piece of software. This is undefined when 3 cosine t over 2 minus 5 sine t over 2 equals 0, or when tangent t over 2 equals 3/5, or t over 2 equals arctangent 3/5 plus pi k, where k is an integer. If t is to be between 0 and 2 pi, t can only be 2 arctangent 3/5, which is where we examine this antiderivative formula. The viewer can verify that as t approaches 2 arctangent 3/5 from the left, The denominator approaches 0 from positive values, while the numerator stays positive, so that this fraction tends to positive infinity. Therefore, the arctangent of the fraction will tend to pi over 2, and 2 times the arctangent will tend to pi. As t approaches to arctangent 3/5 from the right, the viewer can verify that the denominator this time approaches 0 from negative values, while the numerator stays positive, so that this fraction tends to minus infinity. The arctangent will tend to minus pi over 2, and 2 times the arctangent will tend to minus pi. The difference between the limits on these two branches is pi over 6 minus pi over 6, or pi over 3, so we add pi over 3 to the second branch to ensure the existence of the limit at t equals to arctangent 3/5. To make the antiderivative continuous, we assign to t equals to arctangent 3/5 the value that is the limit at t equals to arctangent 3/5 along the two branches, and this is 1/6 times 2 arctangent 3/5, or 1/3 times arctangent 3/5, plus pi over 6. At t equals 0, cosine t over 2 is 1, whereas at t equals to pi, it is minus 1. Sine t over 2 is 0 at both values of t, so that when subtracting the value of the antiderivative at t equals 0 from its value at t equals to pi, we get 2 pi over 6 plus pi over 3, so that the value of the integral for the imaginary part is 2 pi over 3. Therefore, the value of the contour integral is 0 plus I times 2 pi over 3, or 2 pi I over 3.